Lab 3, Circuits by Dhilan Nanji. Here are the contents for this presentation. Introduction. The purpose of this experiment was to predict and measure the behavior of circuits containing batteries, resistors, and capacitors using Kirchhoff's rules and Ohm's law. The experiment. The Circuit Creation Kit AC Virtual Lab by Colorado FET was used to simulate multiple circuits containing batteries, resistors, and capacitors. The system is the circuit, including a voltmeter is attached, and the surroundings is everything outside the circuit. Ammeters and a voltmeter were used to measure the circuit and voltage for a variety of conditions. Current, not circuit. Main results. The total potential difference around the circuit, in accordance with the loop rule, was 0 volts. The capacitor in the circuit with the 10 ohm light bulb took 8.1 seconds to charge and 8.0 to discharge. The capacitor in the circuit with a 20 ohm light bulb took 13 seconds to charge and 14 seconds to discharge. The calculated time constant from the voltage over time data was about 6, which agrees with the predicted result from multiplying the capacitance by the resistance from the circuit parameters. Introduction. Key concepts and math models. Kirchhoff's voltage law, or the loop rule, is the total potential difference around a loop in a circuit has to equal 0 volts, and this equation is shown to the right, as well as the next two. Kirchhoff's current law, or the node rule, states that the current entering a node or junction is equal to the current exiting that junction. Ohm's law is the relationship between voltage, resistance, and current, and the time dependence of the voltage on a discharging capacitor measures the voltage of the capacitor as it discharges over time, and that is relevant later in the lab. These are the initial conditions for each portion of the experiment. On the top left is 2 resistors and 2 1.5 volt batteries. The top right is a resistor and ammeter in series. Bottom left is one 200 millifarad capacitor and a 10 or 20 ohm light bulb and a 9 volt battery. On the bottom right is a 1 9 volt battery, a 30 ohm light bulb, and one 20 millifarad capacitor. For the first circuit, both I1 and I2 are 0.02 amps. This was calculated using Ohm's law and the steps to the left. Reversing the leads on the ammeter is not possible in simulation, but should give a current of negative 0.02 amps. Replacing one of the ammeters with a voltmeter opens the circuit, making the remaining ammeter read 0 amps since there is no current flowing. There is still a voltage difference between the two wire ends, which is negative 3.00 volts. This is because the wire ends are connected to an end of the battery, which is the source of the potential difference. Each wire end is essentially an extension of the battery terminal it's connected to. After closing the circuit with the wire, as shown to the diagram to the right, the potential difference between each two adjacent points can be taken. AB is 3.0 volts, CD is negative 0.96 volts, EF is negative 2.04 volts, the rest are 0 volts since they're on wires and meters. The total of these voltage differences is 0 volts in accordance with Kirchhoff's loop rule. Using the potential differences and Ohm's law gives the following resistances. The 47 ohm resistor is 47 ohms, the 100 ohm resistor is 100 ohms, and the wire ammeter resistances are 0 ohms. Attaching a voltmeter does alter the circuit, but does not significantly alter the current, since a voltmeter ideally has an infinite resistance, therefore making current not flow along the new path it creates. This is also why one cannot be used to close the circuit as we tried earlier. Modifying the same circuit, we can place an ammeter in a series with 100 ohm resistor. This creates a new path with no resistance, and the ammeter on the path with the resistor reads 0 amps. This is because the current will always take the path of least resistance. In addition, the other ammeters read 0.06, an increase, due to this loop of the circuit having the same voltage and lower resistance. The circuit on the left was used to determine how a capacitor charges. When the light is connected to a battery and capacitor in series, it starts at its maximum brightness and dims until it is no longer on. When the battery is disconnected and the capacitor and light are connected, the light starts at its maximum brightness and dims until it is no longer on and the capacitor is fully discharged. The current decreased while the capacitor charged from 0.90 amps to 0 amps. The capacitor in the circuit with a 10 ohm light bulb took 8.1 seconds to charge and 8.0 to discharge. The capacitor in the circuit with a 20 ohm light bulb took 13 seconds to charge and 14 seconds to discharge. The switch and disconnected wire are present to make the process of connecting a disconnected battery more convenient and less prone to error, and the light bulb was swapped out in between trials. The final circuit in this experiment was used to measure the time-dependent relationship between time and voltage in a capacitor. The natural logarithm of the new voltage divided by the initial voltage at each point in time are graphed, and the slope of the line was set to equal to negative 1 over RC to solve for the time constant RC. The CK Circuit Creation Kit RC was calculated by multiplying the resistance of the circuit by the capacitance of the capacitor. Both time constant values agree. The calculations and graph are on the right. as well as the circuit used in this simulation. Conclusion. Since this was a virtual lab, sources of error are minimal. However, human errors such as accidentally clicking buttons in the wrong order as possible could have affected the results. For the first what-if question, if the lab were done in real life, all wires and ammeters should have some resistance, which would lead to a lower measured current. For the second what-if question, an ideal capacitor would charge instantly or near instantly in the absence of resistance. The real capacitor would charge slower due to resistance in the battery and wires decreasing the current and slowing down the accumulation of charge on the capacitor plates.